Alrighty, class. So for today's lesson, we are going to look at 8.3 similar right triangles. What you may have noticed is that in the previous lesson, we actually went over 8.4, and now we're going back to 8.3. And that's because we have an exam, of course, in between, or rather, we had an exam, so we had to make sure that we covered the stuff that we did need. And so we kind of brushed this off. But it's still important. We're still going to talk about it. We're still going to make sure that we understand this concept as well. And so we look at this first key point here, right triangle similarity. And it basically just tells us that, well, if we were to have a triangle like ACB, okay, notice how I'm saying it, ACB, and we find the altitude of C connected to a point called D, right? We actually create two new triangles, okay? And so what this is going to tell us is that all three of the triangles that we had just made are going to be similar in some way, shape, or form, okay? And that's exactly what this part right here says, is that each one of those triangles are going to be similar. And that's actually really important for us to know, because then we can solve for each part and everything like that. And something right here that we need to make note of is to make sure that all letters are in the correct order, okay? Because if they're not in the correct order, then we can't say that they're similar. Similarly, as if we were looking for congruency, okay? In example one, identify the similar triangles in the diagram. Notice that we have this large triangle RTS, and then we split it up into two other triangles with the altitude there. And so now we're going to take those three triangles and show that they're actually similar to each other because of our theorem. And so if you look here on the right-hand side in this green, all the green stuff is basically stuff that I've already gone in and put in there just for us to kind of move things along a little faster. But this first part here, start out at 90-degree angles, then goes clockwise. Okay, I think it's gonna be a really good tool for us so that we can define our start point. And I think it's gonna make things a little bit easier for us. So if I were to do that, let's make sure of a couple things. Let's start at, let's start with our really big triangle. So let's start with the TRS. A triangle, right? If I look here, I know TRS is the larger of the triangles. T is my 90-degree angle. Then I go R. And then I go, not S, oopsies. Or not U, rather. TRS, like so. Then I'm going to say that that one is similar. Actually, I'm going to try to alternate some of these colors so that we can really see where all these triangles are popping out of. Let's go with this triangle next. We start with that 90-degree angle. Start with triangle U. And this is where it can get a little dicey. Sometimes it'll work with the clockwise method. Sometimes it won't. And so here, we want to make sure that we are identifying the correct angles, right? Acknowledge this, right? Angle R is going to be congruent with angle R, right? It just makes sense. It's a standalone angle. It's not even connected to anything else. So let's make sure that we give angle R connected to itself. So U R and then T. Okay. Just make sure that all the angles are matching up together as they should be. Next, let's do this next one here. We have UST, and this is a little trickier, right? Because it doesn't explicitly tell us that this is the right angle, but we know it's a right angle, or sorry, a right triangle, because we know angle UST is going to be right because it's supplementary with RUT. Okay, so after we acknowledge that that is a possibility for us, we can say, well, I'm starting at that U again. So U. And this is where it gets a little bit trickier, right? I look at this, and if I'm going based off the diagram that is provided to us, right? We know that the angle T in that triangle tapers off a lot quicker than angle S. And we know that some of these other angles are kind of tapering off a little bit more as well. Let's just call this one UST. Actually, I apologize, not UST. We want TUTS. My mistake. Yeah, it gets a little tricky with all those different kinds of combinations there. Okay, so you really, really need to make sure that everything is. No, actually, I'm looking at my notes again, and I got things a little bit backwards. You know what? That's okay. We're not going to restart this recording. I'm already a couple minutes in. But, you know what might be the best way to do this would be to redraw the entire thing. Okay, I know it sounds tedious, but work with me here. Right. If I face all of my smallest angles to the left and my right angle on the bottom right, let's say like this, where this is angle U, this got to be S, this got to be T, and I do the same thing with the other ones. Where this is also U, R is the taper, and then T is up there. And then the last one, where T is the right angle, R is still that taper, and then S is out here. Okay. So you know what? On the right-hand side where I say go clockwise, just ignore that. Okay. But we're still going to start that 90-degree angle. So let's just kind of erase this stuff here and just make sure that everything's going to work out for us. Okay. So now that I've written everything out in a way that I can associate these angles and whatnot, I'm going to write them in the way that I see them now. So I'm going to start at T. I'm going to go to R. I'm going to go to S. Okay. Then I'm going to start at U. I'm going to go to R and go to T. And then from there, I'm going to U, T, and S, which I look at it and I'm thinking, didn't I just make this? And I'm pretty sure I just made this, and maybe the clockwise thing does work, but I think drawing the triangles out and putting them in the right orientation is going to be the easiest way to do it. So that's what I would recommend. Okay, don't just try to go off of what the diagram shows. Try to actually make the 3 triangles and then decide from there what to do with it. Okay, that's my recommendation for you. So I apologize for making that more confusing than I should have, but you know, that's okay. We do these in one take, so you'll see the mistakes kind of filter through sometimes. Okay, so then we get to key point 2, and there's a lot of stuff here. Like a lot of things here. Okay, always relabel triangle. Okay, this one obviously is not labeled, so it's there just for us to label. And so we're gonna label it A, B, C as the vertices, and then we're gonna put D right there. That's how we'll relabel this. And as you can see, we're looking to find what CD equals, the X value there. But we do know what AB, or sorry, AD and DB is. And if we look at theorem 9.7, where it's called the geometric mean altitude theorem, here it actually allows us to find what that CD value is. So if I redraw this or reestablish how I'm going to approach this problem, right? I have CD squared is what I'm looking for, equals AD, which is the bottom, so AD times DB. And what you'll notice is that these diagrams are carbon copies of each other. They're pretty much exactly the same. And so I'm going to replace the values I know. CD, replace with an X. It's easier to write X than CD. AD is 6. DB is 3. I get X squared equals 18. X equals 18. Or sorry, the square root of 18. And of course, the square root of 18 is 9 times 2, which will simplify to X equals 3, the square root of 2. Okay. Something I forgot to mention at the very top is that these three formulas, so this formula and these two formulas, formula that we'll see in a little bit, are actually already in your reference sheet, so you don't actually have to memorize these. It's already in your reference sheet called geometric mean. You'll see it on the bottom of our reference sheets. And you're going to use these formulas to solve for X whenever you don't have a special right triangle. Okay, remember we, at this point, wouldn't have known about our trig ratios yet, and so this is that kind of in-between step. But it's useful for whenever we have similar triangles. Okay, in example 2, this problem, we need to first establish, look at our CFS, are we trying to find a leg or are we trying to find altitude? Okay, here, it's very clear to me that we're looking for a leg. And so if I'm looking for a leg, I need to plug in the correct equation. Okay, the equation I used in this previous example was the first one for 9.7. But now I have a formula for 9.8. Okay, because I'm looking for the leg, right, and this is called the leg for the geometric mean theorem, this is what I have to do. I have to take whatever the leg is, put it equal to an adjacent side, it looks like, and then a whole segment. And so all of that mumbo jumbo there, right? Basically just to say that I need CB, or rather, I gotta, of course, I cannot do this. All right, gotta relabel first. Make sure that we relabel before I just kind of tell you everything we're gonna do and then you not know what we're talking about. Well, we relabel, we want to find what CB equals. Okay, so we're gonna put CB squared. Then what we're going to do is we're going to say, well, I need to know what CB equals. I do know what DB equals, right? That's my adjacent side, part of my same base too, right? And we're only going to use the one of our side with the altitude attached to it, okay? We can't use CA because we don't have two values for CA, but we do have two values for AB, one being BD and the other one being DA. So I'm looking for DB, or not looking for DB, I'm going to use DB to help us here. Then I'm going to multiply by the whole segment, which is FB. And in doing so, I say, well, I'm going to replace all the values I know. So CD squared, or CB equals Y squared. DB is 2. You got to be careful here, right? BA is the entire segment. So I'm going to take 2, I'm going to take 5, I'm going to add them up. 7. Y squared equals 14. Y equals the square root of 14. And that's it. That's actually our answer. Pretty simple. Extra example 2, I'm just going to skip. Okay, I'm probably not even going to talk about it in our lesson. But extra example 2, you can skip unless you want to find some challenge. So this was definitely a challenge problem. If you want more of a challenge, you can use that. On example 3, what I recommend is you redraw the problem because I know it's going to look not as good on your side. But of course, mine looks mostly fine, so I'm going to just leave it as such. But always, 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 always redraw. Okay? Now with this problem, this is a weird problem. It doesn't give us any key points. It doesn't tell us anything about this kind of problem. It doesn't say anything. And so whenever we look at this problem, we're thinking, I don't know how to solve that, right? Because beforehand, H here is my altitude. And I was able to find my altitude with using ZW and ZX, at least for this problem. But here, I can't actually use that because I'm only given ZX. And there is a way around this. And remember, I mentioned that there was another formula that we can use. It's on our reference sheet. And this is that such formula. But before even all of that, we're going to relabel these points because I don't like X, Y, W, and Z, all that. I don't like it. So let's replace these values. So let's call it A, C, B. We'll call this point D. Okay. And in order for us to find what CD equals, we're going to use that formula. Again, it's at the very bottom, and this one's in the right-hand side of the bottom, called the hypotenuse. Okay, I'm not sure why it's called a hypotenuse, but it is under that geometric mean. But what it says is that CD, the altitude CD, is going to equal the leg AC times the leg CB all over the hypotenuse AB. Notice I have all those values here. But if I plug everything in, I don't know what CD is, but I know it's H. AC is 5.5. CB is 3.1. And AB is 6.3. I plug that into a calculator. I get H equals 2.706. But remember, we are using units here, so we're going to make sure we put meters because that's our units. And actually, that problem is really easy to solve. Just, again, just very odd that it doesn't provide us anything else other than anything else in regards to a key point or a theorem or anything like that. So it is what it is. But that's example 3. Extra example 3, of course, always try things on your own first and then come back and we'll review. In this problem, I'm missing a leg of my bigger triangle. And notice that, I know how to, or rather, again, the triangles get really mixed up, but notice here that I do have a triangle, RWT, where X is the hypotenuse of that triangle. And I can actually find what the hypotenuse is. And actually, you can find what the you can find what the value of X is using Pythagorean theorem too, but why go through the trouble of finding Pythagorean theorem whenever we have an equation that makes it actually a lot simpler for us? Okay, I'm going to show you both ways, just because I know that this is an easier one to go about it with, and it gives us enough information to solve it. But let's think about this, right? If I'm going to solve it the geometric mean way, what it's telling me is that I'm going to take these here labels, and I'm going to relabel them first, because again, I really don't like this. Let's say it's A, let's go with B, C, and then we'll call this one D. But after we relabeled, that's fine, right? It says again, we're going to use that previous formula. We're going to say CD equals one of my legs, which is BC, times my other leg, which is AC, all divided by BA, my hypotenuse. Of course, I already know some of these values, so 23.1 equals 25 times X over 65. I'm going to solve for X, multiply 65 on both sides. I get 1501.5 equals 25X. And solving for X, I get 60.06. Looks like I'm using feet. So feet. But what I was saying earlier is that I can actually solve this with Pythagorean theorem, right? I have this triangle right here, the one in blue here. I have a leg, I have a hypotenuse, and I'm missing another leg. So 25 squared plus X squared equals 65 squared. Man, those numbers are huge. I don't want to deal with squares of these numbers. And I'm just saying this on the fly too, and I actually don't know what these values are, but I at least know 25 squared is 625. And then X squared. And I'm not really sure what 65 squared is, actually. Let me go ahead and check my calculator real quick. And that's 4,225. And so if I solve for X, I subtract 625 on both sides. x squared equals, oh man, 0, 0, carried 1 over, there's a 3 for a thousandths, and 360,000, somewhere along there. Actually, now I'm looking at it. Something's a little bit off, maybe. That's right. No, my math is right. Odd. But whenever you do take a square root of 3,600, you do get 60. Again, I prefer the one in purple. I think it makes a little bit more sense. It's a little bit easier for us. But if you can use Pythagorean theorem, go right ahead. But that's completely up to you. If you go ahead and move on to example 4. Example 4 here is very similar to example 3 and actually example 3. However, it makes things a little bit different. And notice that I'm missing a side where I have W feet. But if you actually read it, right, we want to approximate the height of the gym, or rather the gym wall. So we had to figure out what that W value is. And so if we solve for W, we write it over here, solving for W on this side, right? I know what my altitude is. My altitude is 8.5 feet, but I keep forgetting, Make sure that we label everything correctly. You can use your own labels if you'd like. However, I'm going to stick with this approach. So I know my CD squared, that's going to equal BD times AD, right? Using that first theorem that we learned today. And I already know some of these values, so 8.5. That, oh, hello. Not sure why Siri kind of barged into this conversation between you and I, but we'll see her way out of here. Okay, or rather, not 80. I don't want to put 80. I want to put W. There we go. So I know 8.5 quantity squared, right? It's not just going to be 8.5 squared. It's 8.5 quantity squared. Okay, make sure you make that distinction. So I'm going to have 72.25 equals 5 times W. And then obviously you're going to divide by 5. You're going to get W equals 14.45. But be careful. Don't rush this answer, right? We know that this is the answer we got for W. But we're not looking for W. We want the height. So we're going to take W 14.45, which then is part of a wall. Then I'm going to add it with the other part of the wall. And I get a final answer of 19.45. Just like so. Super quick, super easy. Nothing too shabby. Of course, try extra example 4 on your own first, and then we'll come back. Okay, so I'm going to relabel this. I remember this time. Relabel everything here. Of course, these pictures always look so pixelated and grainy and weird. It's just, I don't know, it's weird. But I'm trying to approximate the height here. And well, I look at this problem and I say, well, I don't know. And you know what? This is really unfortunate. I have just realized that I'm not sharing my screen. So you can't see any of this. And I've been recording for about 25 minutes. Again, we always do everything in one take. So let's see. We're going to quickly change that. Again, I really apologize. But frankly, I don't I don't want to record all this. But here it is, right? Kind of talking about all this stuff again. let me just kind of rehash everything that we already talked about. Key point one, this is where we're going to make sure that all of our triangles are oriented in the right way, make sure that all parts are correct and whatnot. So you want to draw your three triangles, set them up similar to each other, make sure you do all that. Start at 90 degrees, it'll make things a little bit easier for you. That's our first key point and example. Key point two here, we have an introduction to a couple of different new things for us here. And so we're able to say all of this stuff, all the nice things here, right? Again, all these here are already in our reference sheet, so you don't have to memorize any of this, but you do need to know when to use them. Then here's our first example. So if you're kind of following along, at least auditorially, then you might have been able to do it. But here is the video now. Then skip extra example 2. Example 3 is that weird thing where we talked about where the key point is not available or something like that. Like it doesn't have a key point for whatever reason, but this is the problem. It's a very similar problem for extra example 3. Example 4 is where we just left off, where we just found that height of the gym wall there. And then now we're at extra example 4, which you can actually see now. Again, I really apologize for that. But I'm really not wanting to re-record all this stuff. So, and now that we've definitely figured that out, made sure that everything's getting recorded correctly, here's the problem that we have. We want to approximate the height of the monument. And we have some tourist person taking a picture here. And so a lot of us are going to look at this and be like, I have zero clue how to solve this. And you'd probably rewrite for about 5 seconds. But realize here that I actually have a leg, which was CB. And I know CB squared is equal to DB times AB. And AB is what I'm looking for, right? That's my X if I had to give it a variable. And so I'm going to go ahead and give it a variable anyway. This is my X. And so if I take this approach, I can actually solve for that. I know I have CB squared is equal to that side BD times the entirety of the whole side. So AB. I know what CB is, 9.5. Quantity squared equals BD, which is 6, times AB, which we don't know, we'll call it X. And we'll just solve from there. 9.5 squared is 90.25 equals 6x. Divided by 6x, or 6 on both sides, we get x equals 15.04 and 2. And of course, this is feet. Okay. So again, really do apologize for not having everything set up correctly, guys. But this is pretty much what 8.3 is. And yeah, so that's it for this problem, or for these this section. I'll go ahead and make a disclaimer in the description of the video, so that you know for the first like 20 minutes it's just me rambling on and talking. It seems like, in the last couple minutes are actually legitimate, working on the problems and whatnot. So again, sorry, but we're all good here. With that, I'll talk to you all later. Happy studying.